So it's my pleasure to be here today, and I'm going to talk a bit about federated learning at scale. And so I thought, it's a summer school, so happy to make the talk or the presentation today very interactive. If there's questions at any point, please stop me, and we can go into more detail. I also wanted to begin by just acknowledging that some of the things I'll talk about today and I guess the work I'll be presenting is really, well, the views also that I'll be presenting have been influenced by a lot of people, a lot of colleagues and collaborators, and I wanted to acknowledge them up front and thank them. So there's a bunch of people listed on this slide who are either co-authors on some of the papers that will be discussed, many of whom, the first two columns, are colleagues at Meta, and also Krishna and Samuel were interns last summer, and Peter Rich-Tarek was a collaborator. He's the PhD advisor of Samuel. So just really grateful to get to collaborate with a lot of these people on this work. So I'm going to start really from a high level and get into federated learning. Maybe I could actually start by asking who's familiar already with federated learning? Who's heard of this? Many hands go up, but not all, which is good. So I am planning to kind of start really from the fundamentals, maybe from the very basics, and keep the talk to a large extent conceptual today. But stop me at any point if you do want me to go into more details, or I'll also be around. I'm happy to go into more details offline as well. So, and I was fortunate a couple weeks ago to be on a panel at the ICASP conference talking about federated learning, and there Vince Poor was the first panelist to speak, and he gave this nice overview, and so I thought I would take some inspiration from him about how to kind of set the stage for federated learning. So the starting point we'll start today with is machine learning in the cloud. So we know over the past more than a decade, there's really been tremendous progress in AI and in machine learning, and applications that are really deployed and that are interacting in people's lives every day. And some of the things that have enabled these advances are increased availability of data, so often being collected over the internet, significant increase in computational power. We have accelerators like GPUs, TPUs, IPUs, the list keeps on going. And so this combination of data and compute has really enabled this revolution. On top of that, we also have open source software frameworks, things like PyTorch, TensorFlow, JAX, and these enable all of us essentially to jump in and try things out and experiment and build on the work that others have done. And so the standard way that machine learning is deployed in the cloud today really is assuming that data is going to be collected in the cloud, so all the data is transferred into the cloud. We do training and we do inference in the cloud, essentially in a data center. And then, when you deploy an application, the inference is going to be done in the cloud as well, so people will essentially all the interesting things are happening in the cloud. And that enables things to be done in a relatively clean way, in a relatively simple way, as we'll see. There's a lot of applications, though, today, where that might not be the most appropriate or the most ideal way to do machine learning anymore. And this is why I think the summer school and the organization here, is a great one. It's very timely to be talking about machine learning and AI at the edge. So we know that quite a lot of the data that is being used in machine learning applications is produced at the edge, whether it's on your smartphone, if you have a smartwatch, if you have a home assistant, AR, VR glasses, if you're getting into the metaverse. And with all this data being produced at the edge, there's increasing concerns or interest in privacy and security of data. And this is across many sectors. So of course it includes technology services, like Facebook, Google, Amazon, many others. Of course, in healthcare, data is very sensitive. Finance, smart grid and power systems, and I've just listed a few here. And of course, this list goes on. And all of these motivate bringing some of the learning closer to the edge. So for privacy and security reasons, we may no longer want to ship all of our data up into the cloud. And so this is really where we get to this point today. So let me talk through two kind of stereotypical use cases here to sort of set the stage, and then talk about the plan for the rest of my two talks this morning. So the first very stereotypical use case is a smart keyboard, right? And this is kind of the one that Google used when they introduced this idea of federated learning. And so, a smart keyboard, when you're typing, it's kind of guessing what's the next word that you're going to type, or it's maybe suggesting what might you be trying to type next. And this is essentially what we call a language model in machine learning, doing next word prediction. We know that language is complex, and it's also constantly evolving, so people start using language in different ways. They start introducing maybe new words or new, anyways, things that they're typing, maybe not a real word, but things that we use to communicate when we're sending texts back and forth. And so we could train a model offline on pre-existing data, but we expect, of course, that if we can train on newer data, we're going to learn new things about the way that language is being used. And we might be able to make better predictions. Of course, what you also type and send in messages to your friends is private, right? And so you don't want that data necessarily going into some language model, at least directly on its own. And so the idea here would be that a large population of users could federate, they could somehow collaborate together in some understood way to collaboratively train a model. Each user in this case might have a relatively small amount of data, or in fact there might be kind of a high amount of variability, you can imagine too, in the amount of data that each user has, depending on how much they use this smart keyboard feature or how much they type and send messages to each other. And in general, we'll see that this is maybe one aspect that will influence federated learning, so different users can have different amounts of data, depending on how much they use a given feature or use an application that is using AI or machine learning under the hood. So each user has a small amount of data. That data is private, so they might not want to reveal that data to the server necessarily. Data can also be noisy. People make mistakes. People don't necessarily, they might try to play with the system to game it or even be adversarial. There might be intermittent availability of the end devices. A device might be available and then it might run out of battery, or the user might turn it off. Or there might be other constraints under which we might say we don't necessarily want to train a model right now because the user is doing something, and if we start training, we're going to eat up all the battery or eat up their bandwidth, or otherwise use processor resources which are going to degrade that user's experience. So intermittent availability might be very different than training in the cloud where your GPUs or your servers are plugged in, always on, and pretty much there to do the computations for you whenever you would like. Of course, these devices are also lower power, they have lower capabilities, their processors are not going to be as strong as the types of processors that we have in the cloud, they won't necessarily have as much memory, and they're also communicating over lower bandwidth and higher delay communication channels. So these are just some characteristics of this kind of a smart keyboard device where we're training on the device itself. Okay, that would be use case number one. Use case number two, let's consider now a bunch of hospitals that are gathering medical data. Again, these are both hypothetical use cases. And so in a hypothetical use case like this, hospitals might be training a model on patient data. Of course, the patients might have consented to having their data used to train that model. And there's a lot of regulations around how this should be done correctly. And each hospital is going to have some good moderate number of patients. But of course, they might expect that if they could, as we know in machine learning in general, the more data that you're able to get access to, typically you can train better, more predictive, more accurate models. So there would be benefits for them to collaborate somehow to pool across the data that they have available if they could be done in a way that preserves privacy, because of course this data can also be extremely private. And so again, we could imagine creating a federation of hospital servers to train a joint model. And so they're going to have some protocol by which they communicate with each other and they try to train this model, at the same time ensuring that the data of each institution remains private and secure. Now, in contrast to the previous scenario that I mentioned where training was happening on device, things might be a little bit different in this medical data scenario, right? There might be, training is occurring on servers at the hospital, not on smartphones. Those servers are going to be plugged in, so they should have relatively reliable power. They might have also plugged in Ethernet, so they would have reliable, somewhat higher bandwidth, lower latency networking or communications. And they should be pretty much always available for training, not just intermittently, so they're not just going to go down sporadically. Also, I think it's worth pointing out, one noticeable difference would be that the number of hospitals that might be collaborating in a scenario like this is probably quite a bit smaller than the potential number of smartphones of different users that could be collaborating to train the language model. Also worth keeping in mind. Good. So federated learning comes into the picture at this point. It was introduced in a seminal work by McMahon et al., a group out of Google, and a paper in AI Stats in 2017, which appeared on arXiv the year before in 2016. And they proposed developing systems where different devices are going to collaboratively train in a privacy-preserving and distributed way. The data should never leave the device, so that's going to be one of the features that kind of tries to ensure that we have some sort of privacy. And then we're of course going to have to do additional things on top of that in order to really preserve this privacy. So instead of communicating data up into the cloud and having learning take place in the cloud, a server is going to coordinate, or there might be some sort of coordination between these different devices where they communicate something like a model update, maybe something like a gradient. So they're communicating model parameters or changes in model parameters rather than data itself, and this can be privacy promoting. We're not communicating the data directly. We're going to see it's not sufficient on its own. You have to do some additional things on top of that, but at least it's one step towards privacy preserving training. There's going to be several other challenges, like we said. The data in the system are heterogeneous. If we think about smartphones, people have all sorts of different models of smartphones, each with different capabilities. That's very different than in a data center where you might have somewhat homogeneous standards of the compute servers that you have in your cloud. There's going to be additional communication overhead compared to when we're in the cloud, potentially. So there's all sorts of things that we have to address. So I'm going to try to step us through in a bit of detail in the two talks this morning about federated learning. In the first part, I'm hoping to give an overview of some federated learning algorithms, and then in the second part, I'll talk about scaling efficiently and try to share some of the experience that I've gained through working with that long list of collaborators at Meta, trying to scale up some of these systems to train models on devices with up to hundreds of millions of devices. Systems with hundreds of millions of devices. So that's scaling efficiently with asynchronous training. Okay, so first part. And again, at any point, feel free to stop me. And if you have questions, don't hesitate. So before getting into federated training, and again to contrast, I thought I would mention a little bit about learning and distributed optimization to set the stage and to understand, because of course at the end of the day, training is optimization, so let's make sure we're all on the same page here. Okay, so learning is often formulated as empirical risk minimization. Now I'm just going to start by talking about learning in a centralized setting where we have all the data available, and then we'll progressively see how the picture changes as we go to a distributed setting. So we have some collection of training data. Let's say we have M training samples, and for the most part today we can talk about supervised learning. So I have some input xi and a corresponding label yi for each of my training samples. And typically I'm considering some parameterized family of models. So where I give the model has some parameters theta, I give it an input x, and it's supposed to output a prediction y that's going to be close to the label in my data set y. So I'm assuming that this data comes from some distribution. The distribution part is not going to be important too much for what we're talking about today. But this is usually the setup that we consider. And we essentially convert learning into an optimization problem by saying, well, I want to minimize the empirical risk, which is I have some loss function, could be the squared loss, cross entropy loss, things we're familiar with, that measures how close is the prediction output by this model with parameters theta to the true label in my data set. And I want to find model parameters theta, which make these predictions as close as possible on average across all of my training samples. Usual setup, I would guess probably most of us are familiar with this. Okay, good. And of course, this parameterized family of models could be something like a deep neural network, or it could be something like logistic regression. Convex, non-convex, we won't need to maybe distinguish between the details of that today either. But just to say, this could be, think of F as a neural network, theta are the parameters, and we're trying to fit those parameters. Okay, so in the centralized setting, if we want to scale up, scale can come in a few different ways. It could be, when we talk about large-scale training, that our model is very large, and so the number of parameters, d, that we have in the model can be very large. Very large here being, small models these days are on the order of tens of millions. Large models can be up to billions or hundreds of billions of parameters. We'll come back to that. We can also scale up in terms of M, the number of training samples that we're trying to fit the model to. And of course, as we try to train over a larger and larger population, we might expect that the amount of data available to train on is going to grow. So of course there's a long history of work on parallel and distributed optimization, not necessarily considering the federated case, but just saying in general, how do we solve distributed optimization problems? For example, going back to this seminal book by Bertzakis and Tsitsiklis, 1989, on parallel distributed computation, where they talk about a variety of different algorithms, including coordinate descent type algorithms, and also asynchronous methods, which form kind of the basis for some of the work I'll talk about later today. But conceptually, a lot of these methods boil down to the following simple setup. If we want to solve a large problem like this, like this one here, for the setup today, we'll just focus on what we call data parallel training, which is where we're going to think of breaking up these samples, these M samples, into N terms if we have N processors. So we're going to give one subset of the training data to each of my processors and tell them to process that subset, right? And keep it simple. And there's going to be some coordinators, so I'm going to have workers, they each get one portion of the loss, right? So I've just basically taken these terms and broken them up into capital L1 up to capital Ln, given each of one of those to a workers, and the coordinator is going to coordinate. And the simple coordination proceeds as follows, right? So the coordinator says, here's my set of model parameters currently based on based on the training that we're doing. Can talk about doing some simple gradient methods. So the coordinator sends the parameters to each of the workers. The workers computes either a gradient or a stochastic gradient on its data set, something that's kind of like a gradient, sends that back to the coordinator. The coordinator averages those all together and just updates, say in a gradient descent type of way. It's pretty standard, right? And then we repeat that. And of course, in the simple setting, the convergence of this method follows directly from standard serialized or centralized optimization theory, because this is a gradient or a stochastic gradient of this original objective that we wanted to minimize. So this is the same thing as just naively parallelizing gradient descent across all the workers. Good. So we don't even need to worry about any complications in the analysis of this algorithm. We can be confident that it's going to converge to something reasonable if we set the step sizes in a reasonable way based on what we understand about how gradient descent should converge. The main challenges that come up when you try to implement this kind of an approach, though, are there can be communication overhead, right? So the coordinator needs to send and receive copies, or send a copy of the parameters to each of the workers, and then the workers have to send their gradients back to the coordinator. So of course, in the parallel and distributed computing community, there's been a lot of work on efficient ways to do this aggregation, either without a coordinator or essentially by building some infrastructure around the coordinator to aggregate in a more hierarchical manner. And the other challenge can be if there's variability in delays, and we'll come back to that. But if some processors might be slower than others, or if the communication of some workers might be slower than others, that can also be a challenge. But yeah, so these are things that in the standard, let's say centralized, data center type of distributed training community, people have thought about for a long time. How do we, for example, compress these updates or do clever things to alleviate variability and delays and alleviate some of the communication overhead? Okay, so that would be in the standard distributed training framework. So now we get to federated learning. So what's different in federated learning? Okay, so in federated optimization, I think the first point I'm going to hope to get across is it's not just another parallel distributed optimization problem. I mean, it is. We can leverage the things that we know about parallel and distributed optimization, but we definitely need to go beyond that. And the reason why it's not is the primary difference is privacy. This is something which is essential in the federated setting. That's the motivation for doing federated learning in the first place. All data is not going to be accessible in the central setting, right? The way that it was in the data center setting. And so that's going to really limit some of the things that we can do. So in the data center setting, I could assume that the distribution of data at each of my workers was the same, because I could take my overall data set, randomly permute it, shuffle everything up, so that essentially the distribution's all mixed up, and then give a chunk to each of my workers. Well, in the federated setting, I can't do that shuffling because the data can't leave the devices. And each user, as we know, we might expect, it might be natural that different users produce data in different ways, right? If we think back to the keyboard example, the way that I type, right? I live in Montreal. I might be sending a mix of English and French, and depending on who I'm communicating with, and that might be a little bit different than in other places. Actually, in Lausanne, it might not be so different, but compared to other places in the world, that might be quite different, right? And so learning a language model based on my data might not be useful to, say, users in the US, where they're probably only going to be communicating in English. We also cannot communicate updates or gradients completely transparently. So in this data center setting, right, the workers just send their gradients or their updates directly back to the coordinator. In the federated learning setting, we need to be a little bit careful about that. And the reason is there's things like privacy and gradient inversion attacks. And so the picture I'm showing on this slide comes from a nice example of a fairly recent paper by Guy Ping and colleagues, where they demonstrated a method that can essentially take gradients or things like gradients and recover what was happening, what was the data that was used to produce those. So the image on the left here is the original image that the user had, which we would have liked to keep private. And the image on the right, you can see looks pretty close. We can tell what was in that image for sure. If you only saw the one on the right, you wouldn't be too confused about what's in the picture. And that's just obtained by inverting information from that gradient. So we need to be careful about how we do this training. We need to incorporate some privacy-enhancing technologies. That's the solution that gets combined, added to this picture when we start talking about federated learning. And so there's two privacy-enhancing technologies that we use. One is called secure aggregation of model updates from multiple clients. The other one is differential privacy. Probably not going to go into both of these today. Mostly I'm going to talk about secure aggregation, but I'm happy to talk about differential privacy more offline if there's interest or questions about that. Good. Okay. So federated optimization, like we said, is not just another parallel and distributed optimization problem. This key difference is privacy, and so we're going to use some privacy-enhancing technologies. And it is true that on top of that, there are a number of other characteristics of these problems that might be different than what we would normally do in a distributed training setting in the data center. Some of the other relevant differences I'll mention here, and we'll come back to them kind of throughout the discussion today, is there's data imbalance, right? So we mentioned that different users, say in a cross-device setting or in a setting where we're training on devices, different users might use the feature that is giving rise to the data for the model that we're training or the application. They might use this more or less, and depending on how much they use it, that might kind of change the amount of data that's available on their devices. This is different than in the data center setting where we choose how much data we put on each device, and so we can do that partitioning uniformly. Data heterogeneity we already talked about. Different users are going to probably produce data that comes from somewhat different distributions. Device availability we talked about a little bit too. And maybe to be a little bit more concrete about, well, we'll come back to device availability, but there's going to be certain conditions under which we're going to say devices are available to train so that we don't impact that user's experience. Device capabilities, we also talked about having different processing power, different amount of memory, lower bandwidth communications, and systems heterogeneity. So I think these are all relevant and important differences to keep in mind, but I just wanted to express the opinion that, in my view, these all come secondary to privacy. Again, privacy is kind of the first thing that we need to worry about when we're talking about federated training. And just to make concrete also, I think it's also useful to talk about two different scenarios which correspond nicely to those two different use cases that I had mentioned earlier. And those two scenarios, two types of federated learning, you'll see people refer to these in the literature. The first one is called cross-device federated learning. So these two scenarios have somewhat different characteristics, and that's why it's useful to maybe talk about or separate them out. So for the first one, cross-device FL, that's where we're talking about training on device. We might have up to hundreds of millions, or in some cases up to billions of devices that could participate in training any given model. Each one of those devices has a relatively small amount of data, small enough that it wouldn't make sense to try to train the model on its own, that it really can benefit from collaborating with others. They're going to be low power with limited processing capabilities, low bandwidth communications, for example, over Wi-Fi or over a cellular network link, intermittent availability, and because of this intermittent availability and because of the number of devices that are participating in training, Sometimes people also refer to this setting as the stateless setting. And just to kind of expand a little bit on what that means, in a cross-device FL setup, if you're training a model on hundreds of millions of devices, well, the number of steps that we take typically to train a model is only going to be maybe on the order of tens of millions, right? And so what that means is that over the course of training a model, we're probably not going to see any given individual user more than once. We're not going to incorporate their data more than once. We might do this explicitly. We might say, after I've seen the data not the data, but incorporated an update from one user, I'm not going to let that user participate anymore. And so for that reason, it doesn't really make sense to try to maintain any state on that user's device, right? In the sense of, corrections or other things we could do, leveraging information of seeing that user many times repeatedly, seeing updates from that user. The other scenario corresponds more to the hospital scenario that I talked about, and that would be what people call the cross-silo FL, federated learning setting. And there you can think of each hospital as being one silo, or each institution that's participating in training. They're going to have tens to hundreds of devices, right? So many fewer devices or silos that are participating. Each is going to have a moderate amount of data. Again, still, maybe they could train a model on their own, but they're still going to benefit from collaborating with others to get better quality models. In this case, kind of to contrast with the previous scenario, now we're doing training on servers, so we have a bit more compute, we have higher power, higher communication bandwidth. In principle, they're kind of more available, they're not going to go away. And so here it might make sense to use algorithms that are stateful, that maintain some state and leverage that to accelerate training, for example, over the course of time. So as you can imagine, at Meta, where I'm based, so far the cross-device federated learning has been the setting that we've kind of focused on the most, given that most of our users are accessing apps from their phone or other devices. And so the focus for the rest of my talk today is going to be on cross-device federated learning. And so that means I'll also try to keep in mind this stateless setting. Good. Okay. So let's step through now a little bit of what goes into synchronous federated training and how it differs from the types of things that we already talked about up until this point. So the first part is, so I'm going to have the picture where we have clients on the left and a server on the right in the cloud that's coordinating this training. And unlike in the data center setting, right? In the data center, our compute is already there. It's always available and ready for us to train. We tell it, here's the model, here's the data, go. In federated training, our server in the cloud is in that position. It's ready to train and do whatever we ask it to when we want. We're at the mercy of the devices, of the clients. And so it's the clients that are going to indicate when they are ready to participate. And like we said before, we want to provide this machine learning service. We want to be training models, but we don't want the training of these models to impact the user's experience. Otherwise, they're not going to want to use these features where it's kind of defeating the purpose of trying to build the system in the first place. And so usually, a client indicating that it's ready to participate means that it satisfies three criteria. It is connected to a reliable power source, so it's plugged in. It's on an untethered network. So for example, a Wi-Fi network where you're not going to have to pay per bit that you send over the wire or over the air. And it's otherwise idle. The user is not trying to use it to do a video call or to do some other, something else on the phone. Okay, so if it satisfies those three criteria, it's going to indicate that it's ready to participate. The other parts that would go into being ready to participate would be also that it has maybe some data that is relevant to the task that we're training the model for. If it doesn't have data, then there's really probably not any point to have it participate in training. And if any of those criteria ceases to be satisfied during the course of training, then that device is going to drop out. Yes?
Just a curiosity, is the user agreement part of this set of criteria that has to be met for the device to participate in training?
The user agreement part, yes, of course, is also, yes, an important part. So of course the user would have had to consent to be part of training the model in the first place. Thank you for pointing that out. Yes. So I guess that would be tied in with what I was thinking of having data available for training, but yes, user consent is very important. Okay, so if our client ceases to satisfy any of those criteria, then they're going to drop out of training. Once the client indicates that, well, once enough clients indicate that they're ready, then the server is going to be ready to start a round of training in the synchronous setting. And so the server is going to send the latest copy of the model, what we were calling theta k before, to the client. And now the clients are going to perform several local updates. It's a little bit different than what we talked about previously, so let's dig into this just a bit. Right, so previously we said the coordinator, in the data center setting, the coordinator would send the model, workers would compute a gradient, and they would send that back to the coordinator. In the local update method type of setting, what's sometimes called federated averaging or local SGD, each device in this case is going to perform several steps of gradient descent or something like gradient descent locally on its data. Right? And so that's what the equations here are saying without going into the details. We perform S steps instead of just computing one gradient. After we perform those S steps, we look at what's the difference between where we got to after taking S steps of gradient descent and where we started from. Okay, and so you can imagine each device is starting from the same starting point, but they're producing gradients according to their own local data, which is not necessarily from the same distribution. And so as they take those S steps, the parameters at different devices might drift apart from each other. They're going to send these updates to the server. The server is going to average those, and that's what it's going to use to update the model at the server. And so the convergence analysis of this local update method does not follow directly from our standard analysis of stochastic gradient descent. We have to account for things like this drift. But there's been some nice analyses, including from Sebastian Stick, who was here, I believe, when he did that work. In 2018, and roughly concurrently by Wang and Joshi at Carnegie Mellon, also some results guaranteeing that kind of convergence. And there's been a lot of follow-up work and extensions to this line of research over the past 5 years, including, for example, ways to incorporate adaptive gradient methods like Atom or other variations. In this paper by Reddy et al. I'm just listing a few of the works here, but there's actually quite a lot of literature, and I'll provide some pointers to other literature a little bit later. Okay, but these are local update methods. So now each device takes many local steps and then sends this model update back to the server. The server aggregates those local updates, right? But we want to do this aggregation in a secure way. This is one of the first privacy-enhancing technologies that I had mentioned a bit earlier. Talk about how we do that in a moment. So we do this aggregation of those model updates from the server, from the clients, and then the server in this step 5 can update the global model, and then we'll repeat. Okay, so now the question is, how do we do this secure aggregation? And why do we need to do secure aggregation? So the why goes back to what I had mentioned earlier. If we see the individual gradient or model update from one client, remember we can invert that and we can learn something about the client's data. And so the idea of secure aggregation is we want some sort of a protocol where all clients participate, but nobody, clients or server, none of them actually ever sees the update from any individual. At the end of this protocol, they each receive the average or the sum of the updates, but at no step should anybody see anybody's individual model updates. Does that make sense? So that's the problem that's called secure aggregation, and let me just give a brief overview of one way of going about doing this. And I'm grateful to my colleague Ilya Mironov. I'm borrowing a couple of slides from him for this. So again, just to repeat the picture here, we've got devices that each trained some model, did some updating of a model with their local data. Each device has its model update. We would like to send these into the cloud to the server, but what we would like is some intermediate module or some computation that's going to take place so that we know the only thing that comes out of this is the sum or the average, maybe plus some differential privacy noise. I'm not going to go into the details of that. And none of the devices nor the server ever sees any individual delta. They only get the aggregate. And so if you're familiar with cryptographic techniques and secure multi-party computation, or things like homomorphic encryption, that might come to mind as one approach that you could use to solve this problem. And indeed, that has been proposed, and I'll tell you briefly about how that works from this paper by colleagues Bonowitz et al., who are at Google. So in 2017, they introduced a protocol for this secure aggregation, and it works as follows. Here's a simplified overview of how this works. So before the clients, the devices, send their aggregates to the cloud, the way that they're going to try to hide information from the server is the following. So each device is going to send a mask, we'll call it a mask, or essentially it's a vector that's the same dimension as the parameters of the model that we wanted to aggregate together. So this is a vector the same dimension as delta. And they're going to send a different one to each other device. And this is going to happen between all pairs of devices. Okay, and these are random masks. And now what's going to happen is each device is no longer going to send its model update. What it's going to do is it's going to send its model update plus the sum of these masks that it received from all other devices. And you can, yeah, that's the idea. Okay, why is that useful? Yeah.
Sorry, by masking, you mean like sparsely pattern or just like a random?
Yeah, let me be more concrete here. So actually there's a couple things, well, it's really just a random mask. The thing I should mention for this to maybe make sense is whereas machine learning usually operates, like we think of our parameters as being real numbers, the first thing that we do for these secure aggregation methods is there's some sort of a quantization where we first cast our real numbers to integers, and we're going to think of doing the arithmetic for this secure aggregation protocol over a finite field. So I think of, summing over for some prime number q, right? I'm going to take the integers from 0 up to q minus 1, and all of my addition is going to be modulo q. So everything wraps around, right? Same thing with subtraction, it works the same way. Okay, and so now thank you for the question, Dimitri. So everything has been mapped to this finite field. These masks are uniform random samples from that same finite field, right? We can talk about maybe some ways people have proposed to do this over real numbers too. It's maybe still a little bit controversial whether it's the right way to do it, but the finite field is well accepted in the crypto community as being one way to do this, right? And you can think of it, if I start with, I had some real delta that was in this finite field, but I choose a number uniformly at random over the finite field that can take me anywhere else. And so at that point, my information is essentially safe, right? Unless you know the mask that was added to be able to subtract that off, there's no way that you could try to guess anymore what was my delta to begin with. And that's really the core idea happening here, right? But now we've added a bunch of masks, but the reason why we've added all these masks together is under a certain condition. If when I'm figuring out the mask that I'm going to add, I make sure that for each of the other participants in the network, our masks are compatible. One is the opposite of the other. So Mij, the mask that the mask that I sends to j is the opposite, or is -1 times the mask that j sent to I, right? When I add all of these things up, all the masks are going to cancel out, and I'm going to be left just with the sum. And that's how the secure aggregation protocol works. Yes?
You said that federated M is usually used in settings where we have like billions of devices. In this case, if every client is going to communicate with all the other devices, that would incur a huge amount of communication.
Seems very expensive, right? There's a lot of communication overhead. I agree with you. So this was the initial proposal in 2017. So I said that we're going to train a model with hundreds of millions or up to billions of devices. One thing I haven't mentioned yet is not all of those devices are going to participate in every single round, because that also doesn't scale. And so typically you're going to do, in each round, you're only going to contact a subset of the population, or rather, after a subset of the population contacts the server, we're only going to take some smaller number. So maybe 1,000 or a few thousand. So it's still going to be a lot of communication, but yes, I agree with you. And this was V1 of their protocol. A similar group of authors, it's also Bonowitz and collaborators at Google, had a follow-up paper, I don't remember if it was in 2019 or 2020, where they have an improved scheme that directly addressed that question about the communication overhead, where instead of having to communicate between all pairs, essentially by imposing a clever graph structure here, you can get that down to log n. So you only communicate with, if you have n devices that are participating in the round, you only have, each one communicates with log n others. And we still get good, good security guarantees. Yes?
I had a question. So what you're showing is these devices probably need to know about other devices participating in the algorithm. Does this have any privacy implications?
Great question. So the question, just to repeat it so others can hear, is that for this protocol to work, each device needs to have some awareness of the other devices that are participating in the computation right now. And what does that imply for security, if others know who are the devices that are participating in that round? It's a great question also. So I will say the way that this gets worked around in practice, and in fact, that's a really good challenge to have pointed out. In general, it's complicated and expensive to maintain or even to gather all that state for any device to have some awareness of other devices, even if we could do it in some privacy-preserving way. Just the fact that devices are coming and going intermittently makes it complicated to maintain that type of information across devices, let alone to do device-device communication. So the protocols, as described in Bonowitz, are conceptual in terms of what messages should be sent from one device to another. In practice, the way that these get implemented, the way that Google has described how they implement them in a paper also by Bonowitz, first author from a few years ago, is all of this communication from device to device gets bounced through the server. So in a sense, the server does end up seeing everything, but the server relays these messages or these masks from one client to the other, which also raises some questions about security, but again, we'll go there. I'm gonna talk about an alternative approach, which I think is an interesting one, a little bit later. Okay, but yes, I agree that it's a challenging problem to solve, also we should acknowledge. Good, other questions on this? So let me mention, the way that I've described the protocol here also today is quite simplified. If you're interested in this, I recommend reading the papers from that group, because there's a lot more that goes into also this question of how do we deal with devices that might drop out due to this intermittent behavior. Right? You can imagine if one device is in the computation at the beginning of the protocol, and so they exchange the masks with other devices, and then that device no longer participates in the end of the protocol. When we try to aggregate things, it's not going to cancel out anymore if we don't get the right sums there. And so a lot of the details under the hood here are clever ways of dealing with that and ensuring that at the end of the day, if a device drops out, we kind of detect it and we correct it in the proper way so that we get the right result at the end. Good. Well, it's 10 o'clock. Remind me for the time, Tao. What time is the first break? Now? Right about now? Okay. Good. So let me just kind of wrap up this part here and we'll take our coffee break. Does that sound good? Okay. So we talked through the steps of a typical synchronous federated learning protocol up to here. And I had a recap. Yeah, perfect. So just to recap everything that we talked about so far. We talked about privacy being the raison d'etre of federated learning. All right, welcome back everybody. I guess we'll resume. Yeah, so take that out. There we go. All right, so this was the recap of where we left off. I did want to say that please keep the questions coming if you have them as we go, if there's anything that's unclear. And also let me know if this seems like if I'm going too fast or too slow. I feel like it might be too slow, but I don't know for sure. So any feedback on that front, I guess let me know. So, right, we talked about local update methods. And I just wanted to mention before moving on that, like I said before, there's been a lot of work in this area, and I'm going to mention a few extensions that people have worked on related to local update methods. So I'm just going to kind of give you this quick list of references. Hopefully the slides will be made available afterwards if you want to follow up on some of these, but I wanted to be sure to mention some of this work. So the first is we mentioned there's this issue of clients drifting apart, their parameters or their models drifting apart when they do many local steps. And some methods were proposed early on to try to remedy that. One is called fedprox, where they add a proximal term, essentially penalizing if your model drifts too far away from where it started. Another method is called scaffold by Pranith, who was a former PhD student here in Martin's group. And scaffold works by introducing a control variate, and that one, in fact, is a stateful protocol, so it's not necessarily going to be usable in cross-device federated learning, but I think it's a great option for cross-silo federated learning, just to remind us of some of the terminology from before. Another one, which is appropriate for stateful, is this method called MIME, and there the idea is to accelerate training through some momentum variance reduction. So it's using notions of momentum and variance reduction, leads to faster training. Again, I'm not going to go into the details of any of these, but references if you're curious, if you're working on this and want to follow up, this is kind of trying to bring things a bit more up to the state of the art. So we can do faster training using something like MIME with momentum. Another issue that's common, again, without going into too many details, is that different devices are going to have different amounts of data, and as a consequence, they're going to perform different numbers of local updates. And whereas most of the previous theory for things like federated averaging or local SGD had assumed that every client is going to perform the same number of local updates, in practice, that's not what we do. If a device has more data, we actually ask it to perform more steps because we would like it to train on all of that data. And it turns out if you do that without correcting for it appropriately, that leads to some bias. It biases the model to be better or towards favoring the data of devices that have more data. So methods like FedNova and FedLin introduce appropriate corrections to try to compensate for this. And then the last kind of final twist on this slide that tries to bring things closer to practice is most of the analyses in kind of the literature usually assume that each time a client is performing a local update, it's sampling a new gradient independently and identically distributed from some local distribution of data. But in reality, we don't have an infinite supply of gradients to sample from. Each device usually has a fixed finite data set, and if it's going to do multiple epochs or multiple local rounds of training, it's going to shuffle or permute those as it goes through them. And so we have a recent paper called Fed Shuffle, which looks into how do we do this. Oh, thank you very much. Great. And the last reference on this slide is a field guide to federated optimization, which is really nice, and it's a longer expository article by Wang et al. From 2021, which gives a great overview of lots of this literature, including kind of practical aspects as well as theoretical developments. And so if you're interested in getting into the area, I think that's a great place to start. Okay, so like I mentioned before, the first part of the talk was setting the stage and giving some background about synchronous federated learning and the way things have been described in the literature and some motivation for why we would want to do this. And for the next part of the talk, I want to talk about how do we scale to deploying a system on up to hundreds of millions of users and training models still in a reasonable amount of time at that scale. And to lead into that, I think it's good that we take a step back and we do a quick reality check. So already there's some things we have to deal with, right? We talked about before how machine learning usually deals in floating point numbers, whereas that secure multi-party computation approach I mentioned to you for doing secure aggregation, that assumes integers, or really computations over finite fields. So there is that mismatch. And I think that's a mismatch that is still around for essentially the same techniques that I'm going to talk about also in this portion of the talk. It's something worth keeping in mind, and that might be something we try to overcome at some point in the future. But there is this mismatch. Clients are mobile devices, and they can only communicate through the server. That also came up through one of the questions before. How do we route messages to and from, clients don't communicate directly with each other. It's just complicated to maintain that type of information, and also could reveal privacy, and so all of the messaging goes through the server. Clients are flaky. They can and will drop out midway through the protocol. We talked about that too, and so that's why a lot of the additional computation or complexity in the Bonowitz protocol involves how do you handle clients dropping out midway through this secure aggregation. The last thing, and this is going to start to motivate why we want to go to asynchronous processing, is that computation is iterative, right? When we're doing stochastic gradient descent or any type of numerical optimization. Usually we're talking about iterative methods. And in theory, we measure how quickly something converges based on the number of steps we have to take. But in practice, it's also super relevant to keep track of how long does it take to complete each step. And in that respect, latency is really key, right? If we can reduce the time for each individual update or each round in federated learning, that can actually have a huge impact on the time it takes to train a model, as we will see. So we want to be able to complete these rounds quickly. Unfortunately, synchronous methods aren't very amenable to doing that quickly, and here's why. Okay, so let's look at what happens over the course of time. At my server, I've got one model, and I want to perform an update. And let's say that, as we said before, I'm not going to do an update using information from all of the clients in every single round. So for this cartoon example, I'm going to say, let's suppose that I've got 4 clients, and I want to use just those 4 clients to perform the update in this round. So of course, each client needs to download the latest copy of the model. They have different bandwidths and different latencies, and so that might not take the same amount of time for each client. They're going to do their local computations. Again, they have different capabilities, processing-wise. They might have different amounts of data, and so that's going to take different times on each client. And then we need to aggregate, but we can only aggregate once all of the clients are ready, right? And so the total time that it takes to perform one of these synchronous rounds is going to be bottlenecked by the slowest client. The one who takes us the longest time until they've finished their computation and they say, okay, we're ready to do the aggregation. Makes sense, right? And this is common across all synchronous processing, and we know how to deal with it. But in fact, I think in federated learning, in these types of systems, because of the heterogeneity and because of the latencies involved, these phenomenon are really exacerbated to a large extent. So clients are heterogeneous, and just to give you concrete numbers to show that I'm not creating a problem out of nowhere, I can show you some data. This data comes from us training a small language model on the order of, I believe it was 100 million Android phones. And what I'm showing you is a histogram of the time it takes each client to perform an update. Those steps of downloading the model, doing their computation, and being ready to do aggregation, right? And so, first thing I want to point out to you here is that the x-axis is on a logarithmic scale. So there are some clients that are fast. They complete things in under a second. Other clients take hundreds of seconds. So these delays can vary by several orders of magnitude. This is a problem, right? If we look at the mean execution time, it's a little bit more than 1 second, but remember, we typically want to aggregate over some population, and I think in this example, well, let's say it's either 100 or 1,000 clients that we want to aggregate over in each round, and so that means we have to really be worried about the upper percentiles of this distribution, and so that's why if we look at the mean round duration, the time until, let's say it's 1,000 clients are ready to perform this update, that's going to be up on the order of hundreds of seconds. So it's going to significantly slow down how long it takes to do this training, if that's the time it takes us to complete each round. Demetrius.
So, are you able to is the API able to check kind of like the type of hardware and decide who participates according to whether they have a fast or not a fast device?
Let me come back to that, but that's a good point. No, so we could try to use some information and decide who's going to participate based on what devices. If we knew information about the device, we have to see is that something that clients are willing to provide to us. Is it reveals some privacy information, or is that if that were available, we could imagine trying to do something clever, like grouping together clients that have similar capabilities. That might solve part of the problem, but actually, as I'll foreshadow, we're going to see that just filtering on device type or capability would not completely eliminate this. This is actually really due to something else. Yes?
Yes, I wanted to ask, so you said you identify some devices which will participate. Could you hypothetically identify all devices as participating, send the model to all of them, and then take the first which complete several steps?
Yeah, so the proposal here was, if I try to summarize what was being proposed is, so one way you could think of, first let me make one clarifying point. So we're choosing to some extent which devices are going to participate in this round. But remember, what happens really is that the clients tell us when they're ready. And you can imagine we're just going to keep a queue of clients who told us that they're ready to go and that are still ready to go. And at the beginning of a round, we're going to pop off some number of clients from that queue and send off the model to them to participate, right? Now, the proposal was, well, if you really want 1,000 clients to participate in this round, why don't you send to more than 1,000? And then the first 1,000 that get back to you, those are the ones that we're going to use. And in fact, that is how we deal with this issue, or how it's been proposed to deal with this issue. That's not going to be how we deal with it, but that's how it's been proposed in the literature. But I'll try to point out there's some concerns that that can bring up. Okay, back, yeah.
So what's the little spike there at the tail?
What is the little spike? I think it's just noise. This is an interesting thing about federated learning, which is you see things in data, and of course these have been aggregated in a privacy-preserving way, right? Because this is client-private data. In federated training, one of the great challenges is you don't get to dig into the data to try to understand what's going on, at least not easily, right? So we'll chalk it up to noise for now, but yes. Was there another?
I was going to ask the same question.
Got it, the little spike in the tail, yep. Okay, yes, so here's the proposal in a slide, what was proposed here. Let's set some target. The target could either be the number of responses that we want to get, or we could also just set a timeout, a threshold, and we'll say after this point in time, if we haven't heard back, too bad, so sad, we're moving on, right? And so in essence, what that's going to do is that there's going to be certain clients that get excluded from this computation, right? Those clients that take a long time to complete their updates. So aggregation should really start shortly after the target or right after the target, but this is the picture to have in mind, right? Good, so we have heterogeneous clients. We can set a target, and that's going to help us reduce this time because we're essentially filtering out what are called stragglers. Stragglers being the ones that take longer to do this computation. There's a consequence to this though. And a nice way to say that is that clients are different in wonderful and very interesting ways, right? And what do I mean by that? Well, if we go back to our example of training our language model, here's what happens. So if I do basic federated learning, if I don't do any of this filtering, or if I don't do any of my setting a target and thresholding, I let everybody train, but I just let it take as long as it takes to train to a suitable accuracy, let's say, or for a suitable number of steps, takes around 130 hours, right? That's like several days. And the metric that we use to measure the quality of a language model is called perplexity. Don't need to worry about the definition, but just know that lower is better, okay? And so the average perplexity, this is the average over the population. So I take the model that I've trained, I ship it to the population, and I ask them, how good is this model on your local data? And they report back to me in a privacy-preserving way. Average perplexity is around 68. Now, if I look at the perplexity of the 25th percentile, where the top 25 here is 25% of the population that has, you know, the 25% of the most data, right? Are they rich in data, essentially? We do a little bit better on those, but there's really something interesting here if I go up to the extremes. If I look at the perplexity of the 1% of the population that has really the most data, remember, so the most data, their perplexity is substantially lower, right? They have a lot of data. The model makes very good predictions on those users. On the other hand, once I impose this timeout, I say after a certain amount of time, I'm just going to move on. That means I'm essentially filtering out some users. I train much faster, right? I can train in 19 hours now. My average perplexity is a bit worse, right? It jumped up from 68 to 73, but maybe that's something we have to live with to be able to train faster. But if we look again at this 25th percentile or this first percentile now, basically they're only doing as well as the average. They're no longer benefiting from having more data. And essentially what that comes down to is once we've done this filtering, the users that we are not using when we train data are the users that have the most data. And we know in machine learning, the more data that you have access to, the better quality model you can train. And so we're kind of shooting ourselves in the foot by not training not allowing those users to participate in training. Yes?
So it's an optimization problem then where you do trade-off between time to train and to timeout?
So you could say there could be an optimization problem to trade-off where you could vary this threshold and you could sweep over some Pareto frontier. I'm actually going to propose an alternative way to try to get around this. But yes, that would be one way to go about this.
So once you're done with, so this is the classic federated learning, right, where you do federated averaging and no fine-tuning at the end.
Yeah, we'll talk about personalization later on, right?
Because I guess that's the thing I want to understand here, because you could say, okay, you know, maybe Perplexity is bad for that 1%.
But if they
benefits from their own data, you can fine-tune.
That's a good point. So the point that Demetrius is making is we could do things afterwards. We could say, okay, after we finish doing our federated training, for those users that have a lot of data, locally they can just perform some additional updates, and maybe they have enough data that that's going to be beneficial to them. And that's a valid point. That's a valid point. So I'm just going to focus on making the federated part better to begin with. And we'll come back to talk about personalization at the end if there's some time. And remind me, what time do I have until?
15 minutes.
15 more minutes? Okay, until the hour. Okay, I'll do my best. So let's talk about asynchronous federated learning. This is the alternative that I'm going to propose. We proposed this in a paper in 2021, Nguyen et al. And the asynchronous method that we're thinking about here is related to something from a paper in Dutta et al., which I think is called hybrid async there. So the idea is the following. Oops. What I'm going to do is think about, I'm not going to completely remove other users, or I'm not going to force them not to participate by filtering and setting a threshold. I'm rather going to allow myself to be asynchronous. And what that means is I'm going to set a threshold on the number of responses I need to receive before I perform an update. But then I'm going to let others respond later. Okay, so this is also another kind of a trade-off that comes up in asynchronous optimization. So in this example, I have set the threshold to be 3 clients that I need to receive updates from, and then I can perform a model update. So here we've got our 3 clients proceed as at their own pace now. And so when I do this update from model 0 to model 1, I'm incorporating the updates from clients 1, 3, and 4. They all started from model 0. The thing is, when I start to do asynchronous processing, there might be stale updates as well. So you can see the way that we got the update to model 2 was by combining information from client 2, client 5, and client 6. Clients 5 and 6 downloaded the most recent model, so their update is not stale. But on the other hand, client 2's update is based on an older version of the model, and so its update is stale. Right? This is kind of the classic alternative trade-off that comes up in asynchronous processing. How do you handle stale information? Okay. In the most standard asynchronous algorithms described in the previous parallel and distributed computing literature, the server would perform a model update every time it receives an update from any individual client. Right? So every time one client finishes, like the first one that finishes here is 3, it would perform that update, and then we would have a new model instance here. So one of the key differences in the protocol that we're going to be talking about today is that we actually wait and we still aggregate over several clients. And remember, we need to do this for privacy. We don't want the server to ever see the update from any individual because it could invert the gradients, and that's undesirable, right? Okay, so how do we do secure aggregation in this asynchronous way? This is going to be kind of the tricky part here. So clients A potentially started computing from different models, so we have staleness, but we're going to see that late updates are still valuable. Stale updates are valuable, they just have to be maybe weighted accordingly. So if you have updates that are very stale, maybe you don't provide as much weight to them without going into the details, but that's, you kind of downweight based on staleness. So we're going to try to aggregate responses from clients in a secure buffer and only release the aggregated update to the server once enough responses have been received. So then the question comes about, how do we implement this secure buffer? And to do that, we're going to use something called a trusted execution environment. So this is a piece of secure hardware. It's a secure area within the main processor or CPU. But in the secure area, we're guaranteed confidentiality and integrity against the host operating system of that's running on that CPU. Right? So I think the way that Ilya likes to say it is what happens in the trusted execution environment stays in the trusted execution environment. Of course, that's under certain assumptions. We won't go into all the details of the threat model or the security model, but that is the case. And I'll also point out that there are several commercial implementations of these trusted execution environments. Oops, and that should be Intel SGX, not SGD. Certain kind of, yeah. Optimizer slip there. Okay, so let me explain in a cartoon here how we're going to do this asynchronous secure aggregation. Right, so this is in the cloud now. We've got our aggregator, which is the process that was accumulating before this is running on our server in the cloud. It has a trusted execution environment attached to it. And on our device, what we're going to do is the following. So we're still going to convert things into integers and do our arithmetic over a finite field. The device is going to just generate its own mask, and it's going to apply that mask to its model update, right? And so when I draw this little lock here, that's basically saying that is a masked update. Remember that mask was a set of random numbers over this finite field. And so when it generated that random mask, the client knows what key, what seed was used to generate that random mask. That serves the purpose of this key here. Now, it's going to transmit two things. It's going to send the encrypted model update to the aggregator directly, to the CPU. And without going into the details of why, it's expensive, it's more expensive, we incur more latency when we communicate with the trusted execution environment. There's essentially more steps involved in doing that. But we can send this secure key, the seed, over a secure channel, so kind of the same TLS security channel that you use when you're sending your credit card information over the internet to a credit card server. You establish a similar secure channel directly between the trusted execution environment and the device, and you send the random seed to the trusted execution environment, right? And so now we're going to accumulate several of these model updates from several clients, and the trusted execution environment is going to get the key for each one of those. Once we've reached the number that we need to be able to release the model to the server, the trusted execution environment has all of these seeds. It knows the random number generator protocol, and so it can use those to generate the aggregate mask that needs to be added to this aggregate encrypted model in order to get rid of all the masks, undo all of that, and then the server has the overall model update. Make sense? So that's how we do this in an alternative way. So we're not using secure multi-party computation the way that we did before. Instead, we're using this trusted execution environment. To be fair, I did want to point out, kind of we have to make some choice between these two different families of, or ways of going about doing secure aggregation. Each one of them has a different set of assumptions and a different set of threat models underneath it. And so I think that's something that still needs to be discussed about, which is acceptable versus not acceptable in what circumstances. So it's not like they are directly comparable, I guess is what I wanted to say. They make different assumptions, but I think they're two very interesting ways of going about solving this problem. And in the asynchronous case, we know that this trusted execution environment is a valid way to go about it. Okay, and so if we do this now, what happens? Well, comparing to before, when we use this asynchronous protocol, we do train faster, okay? And because we are not discarding or eliminating certain clients from participating, in particular the clients that had a lot of data, we also see significant improvements to the performance across the board. Now, I will say, in this amount of time, part of the reason why we're able to get even lower complexity than before is actually we're able to perform many, many more updates in the same amount of time. So, well, in 18 hours, so in slightly less time, we get lower average complexity, and we also see that if we go up to that top 1% percentile, we've actually managed to do much better. Good. Yeah?
Why are we better than the basic FL?
Yeah, why are we better? It's because, so we had to stop the training at 130 hours in this case, right, things are going, but essentially in these 18 hours, we managed to process even more updates than we were able to in that 130-hour case. So in principle, right, if we had kept on letting this run for longer, it should get to the same levels. Yeah.
So is this actual hours?
Yes.
And did you do hyperparameter tuning or kind of just used?
Yeah, so no, in this case, how we went about, hyperparameter tuning is a whole other can of worms, right? we did not. The way that we handled that in this case was we had some proxy data available in the server. We did simulations to try to find what we expected to be reasonable hyperparameters in advance, and then we used those and crossed our fingers, and it turned out that it worked okay. But that's always an issue, yeah. Yes? Yes. So how do you trust the trusted execution environment? So again, I'm not going into all the details, and I don't have time to go into all the details today. The developing for these systems is more involved than just writing your code and compiling it, is all that I'll say. There's additional things that go into it so that you can, basically the trusted execution environment provides a way to cryptographically certify the code that is running on that trusted execution environment. So the client can do a check. It can do something like public key cryptography. It can pass it a number, and the trusted execution environment is only going to give it the right response if the code that's running on that trusted execution environment is what it says it should be, right? So that's part of what's going on here. Yeah, I think one could do many lectures just on trusted execution environments as well. I think it's an interesting topic, but without going into the details, I'll just sweep it under the table and say it is possible to do this. Yes?
So if I understand correctly, you essentially encrypt everything using normal banking type encryption and send it to the cloud, the thing that's doing the aggregation, right? And then you use this trusted execution environment. That's fine. Why not do the aggregation within the trusted execution environment itself?
Yes, great question. Why not directly do the aggregation within the trusted execution environment? In this case, the motivation not to do it there was for speed. One could do it there as well, and it would be fine, but it wouldn't be as fast. And again, that's because, I mentioned it very quickly, but to get bits into the trusted execution environment and out takes significantly more time than it does just to send them to the CPU itself. And so to speed things up, that's why we were motivated to only send the seed that's used. So it's one integer that gets sent to the trusted execution environment. Once it knows that seed of the random number generator, it can generate the entire mask, and it only has to send essentially one copy of the model out, which is the aggregated mask from all users. So it was a question of speed, essentially. Now, this could change over time. I think the technology of trusted execution environments is still relatively in early stages. If things get accelerated and faster, they would be very viable to do that. I will mention one other limitation of earlier instances of trusted execution environments was that they had relatively less memory available to them. So the newer generations, that's not as much of an issue or concern anymore, but in earlier versions, that was one limitation. Yeah, thanks for the questions. Okay, let's go. So let me wrap up on this part and say heterogeneity gives rise to very real challenges in federated learning. How we deal with it has implications, right? And so setting timeouts for slow users, if those slow users are slow because they have more data, we saw that could be a problem or could be problematic for our models. Dimitri's mentioned, what about trying to do things in a clever way based on the type of hardware if we have systems heterogeneity? I will say you can do that, but also excluding older, less capable devices can have implications for the quality of the model and how it performs on data from those devices as well, and so one needs to be a little bit careful there. So in general, I think being inclusive and embracing diversity is always a good way. Just finding the right way to do that and still have performance systems is an interesting research question. Talked a little bit about asynchronous secure aggregation, and I described to you a way to do that using trusted execution environments as a secure buffer. Shortly after we put out our paper on asynchronous federated learning, another group from the University of Southern California put out an alternative multi-party computation protocol that would be suitable for doing asynchronous aggregation. It's a little bit involved. You can see it as the simplified Bonowitz protocol that I described to you earlier with a lot of additional clever tricks on top to make it work. So there could be alternatives to using the trusted execution environment depending on what one is willing or interested in going about using. And so I'll mention at the bottom here, I've got references to the couple of papers, FedBuff and Papaya, which describes more about the implementation and the systems evaluation at scale. And if you're interested, the simulator that we use to do those simulations and find reasonable hyperparameters, the link there is at the bottom. That's been open sourced. Okay, so I wanted to talk about one other thing very quickly before wrapping up completely, which is something that also came up in the discussions, which is this idea of personalization. I think, and I'm using this to lead into some very interesting open directions for research in this area. So one might ask, why train one model for all that should be good for all of the devices, right? And I think that's a very reasonable question. Personalization tries to essentially train one model personalized specifically for each device, while still benefiting or leveraging some of, from the data on other devices potentially. And I think one particularly interesting direction is what I would call partial model personalization. This is where you think of factorizing your model in such a way so that some of the parameters of the model are going to be shared across all devices. Others are going to be the personalized parameters for your particular model. And so you think of overall having this set of full model parameters, WI, where U is the shared parameters and VI are the personalized parameters. And of course, there's several ways one could think of carving up a model. And so one way would be, say, to have a shared feature extractor, shared earlier layers. Right, so your input X goes into the shared part. Maybe you have a personalized classifier head on top of that, and that's how you output your predictions. You could, of course, flip that around, have a personalized feature extractor, a shared classifier on top of that, make predictions, and you could do more sophisticated things. For example, in the literature, there's something called adapters, which are thin layers that would sit in the middle of your model. In particular, they've been proposed both for transformer type models, also for residual network models. And these are thin layers that make some transformations of the activations as things are going through without going into the details. And I think an interesting thing that we observed just experimentally is none of these is universally the best. Really, which one you want to use depends on the application that you're trying to solve. It's probably not surprising, but this is the case that we found. So for example, for next word prediction, having a personalized classifier seemed to do best. For speech recognition, having a personalized feature extractor did better. And that might also be reasonable. You might kind of expect that if you can transform different people's speech into some common space, then you can do classifications in that space. And finally, for landmark detection, which is more of an image classification task, these adapters worked quite well. So of course, one can also leverage the structure that's imposed or that comes up once you have that shared and personalized parameter partitioning in order to come up with better optimization methods. Alternating schemes versus simultaneous updates is kind of the classic two that we consider in parallel and distributed computing. One can show that in this particular setting, the alternating scheme gets a better rate in terms of the constants, and we also see this play out empirically in some experiments. And so just to kind of wrap it up here, as far as open directions in federated learning, I think personalization definitely is an interesting one and an interesting direction to follow up on. And it intersects with a lot of other things that I talked about today. And so for example, privacy and personalization I think is particularly interesting. I didn't get to talk too much about differential privacy, but one way to view what differential privacy is essentially trying to do is to filter out outliers, right? Because outliers are hard to make private. If everything looks roughly like the population, then kind of that's how we get privacy. And so if you can use personalization to make good predictions on sort of outlying data points, that might be an interesting way to improve some of these privacy utility trade-offs. I think there's still a lot to understand in terms of fundamentals and statistical learning theory for personalization. I think there's also a lot of interesting directions to follow up on in terms of going beyond local update methods. And so for example, there's very interesting work on ensemble distillation from Tao and collaborators here. Another interesting direction you might want to think about is how do we train large models on these tiny heterogeneous devices? We know that larger models, at least in a data center setting, can make super interesting predictions and do be very, very performant. But when we have very limited capability devices, it's not reasonable to try to train, let alone do inference with those models on device. So somehow trying to find the right way to balance all of this is a great research question. Yet another one is, where do labels come from? So for some of the tasks that we were talking about, the user is either implicitly or explicitly providing labels when they use a feature or an application on their device. And in the healthcare setting, there might be radiologists or doctors that are providing labels for us. But in other settings, we don't necessarily have labels on device, but we might have labels for some proxy data on the server. Finding the right way to combine these is a great question to think about. And the last one is, I'll mention just because I think it's interesting, privacy frameworks for machine learning and federated learning. I think we didn't go into differential privacy, but it's not clear to me if you're familiar with it, and you might feel the same way. It's not clear that that is really the right privacy framework to be talking about for machine learning. Happy to talk more about this offline if you're interested. I think there's interesting things to look at also at this intersection of privacy and compression. Privacy, at the end of the day, I hinted at it, the way that you make something differentially private involves adding noise. And we know that compression can be viewed also, at least lossy compression, can be viewed as adding noise as well. And so finding the right way to look at these things holistically is an interesting direction to pursue as well. So with that, I'll say thank you very much for your attention and happy to take more questions, or I'll be around. So yeah, thank you. The question is if I could talk a little bit about the deployment challenges and how do you circumvent them. I'll say, well, one could give a whole other talk just about the deployment challenges. So I don't know that I have time to do it justice in just a very quick response to your question, but some of the things to do with heterogeneity, I think, so I think thinking about how to design the system in a way so that you can, so we know from distributed systems, there's been plenty of work on how to design systems that can tolerate certain amounts of, not necessarily heterogeneity, but unreliability, right? That's essentially what distributed systems deals with. Things can go down. How do we ensure that computation or data is preserved? And so, just at a very high level, I'll say that the answer to your question, in the way that we dealt with scale and deployment challenges, largely comes down to leveraging ideas from that community, thinking about what's the right way to structure the architecture, the framework that you're deploying, in a way so that you can quickly scale out to handle more devices, so that you're robust if one component goes down, so that you are using a heartbeat to make sure that devices are still active and available and that they haven't just vanished, all kinds of things like this. If you're interested in more details, I would refer you to that paper that I mentioned here, Papaya. That's really where we talk about a lot of the structure of the framework that we deployed and some of the ways that we dealt with that, deployment challenges.
Thank you.
Yeah, thank you.